continuous distribution of charges. What is this continuous distribution? Actually, we are considering the discrete nature of charges. According to quantization of electric charges, the charges are of discrete in nature. That means if we talk about different charges, then we talk about Q1, Q2, Q3 till Qn. That means we are talking about individual charges. What is discrete? The discrete is separate charges. Till now, what we have studied, the principle of superposition, the Coulomb's law, all associate with charges that are discrete. That is Q1, Q2, Q3 and so on. But now I am going to tell you that if the charges are very closely spaced, in that condition, let me draw a diagram. If suppose this is a space, okay, I am talking about some space, it can be of any shape or size. In that condition, if there are too many charges, like for example, these are the charges that are distributed in this space, okay. So all this space consists of different charges and so on. Now, if I ask you to look at this particular diagram, if you look at the microscopic level, then that means that you can see every single dot separately. In that condition, this dot become discrete. That is, they appear to you separate in nature. Now, if I ask you to look by your naked eye, that is at macroscopic level. Macroscopic level means looking by the naked eye. So, if I am going to look at this diagram from a distance, in that condition, these closely spaced charges appear to me continuous. It is very difficult for me to identify every single charges. In that condition, I have to use the continuous distribution of charges. Let us suppose if there is a road and there is a heavy traffic in that. Okay, this is a road and there is heavy traffic. That means there are many vehicles which are placed in that road. If you have seen a busy traffic, then in that condition you know how closely spaced vehicles align themselves. In that condition, if I look at very carefully by the microscopic level, I can see every individual vehicle separately. So this is the discrete nature. But if I ask you to look from distance, in that condition, these cars or vehicles which are aligned on a particular road appear to you in a continuous manner. That is, the discrete nature of cars gets lost. And what come into role? The continuous nature of object comes into role. So this is what we are going to discuss. Now we are not going to consider Q1, Q2 separately. We are going to consider whole surface in that all the charges are continuously distributed. This is what we are going to find. In this particular topic, the first word that comes into role is charge density. First, let us understand what is this charge density. The charge density means the density of charges. That is, the charges placed at per unit dimension. Now, what do you mean by dimension? Dimension means any area or any particular cross section. This dimension can be linear, it can be along the surface, it can be along a particular volume. So, what is charge density? The charge density is defined as charge per unit dimension. Now, we are going to consider three dimensions in this case. First, we are going to consider a linear dimension, that is the linear charge density. Second, we are going to consider the surface dimension, that is a surface charge density. And third, we are going to consider the volume dimension, that is a volume charge density. So in this condition, you have to look that if the dimension is linear or if the dimension is along a surface, if the dimension is along a volume, so the charges are so closely spaced and the charges are arranged in so cluster that we are not going to identify every single charges. So we are going to take whole lot of surface. First, let's start with linear charge density. This linear charge density means that charges are distributed per unit length. Linear means along a particular length. So the definition for it, charges per unit length. The linear charge density is represented by a particular term, that is lambda. Now suppose if this is a dimension, if this is suppose a length, okay, we can say suppose a conductor or anything. If this is of particular length, let's say small l, the length of this conductor is small l, the charges are distributed uniformly in this condition. Let's mark these charges as Q. Now the formula for linear charge density lambda is equals to Q upon L. Q is the total charges distributed along a particular length and L is the length of a conductor which we are going to take. Now in this condition, what will be the unit of lambda? The unit of lambda is Q is denoted by coulomb and L is denoted by meter. So lambda unit becomes coulomb per meter. Now this is the condition, this is the formula when I took whole length and whole charge density. If you are going to consider suppose this particular, it is the same conductor of length L. Now if imagine these charges are distributed uniformly all over the length of the conductor. So now if I am going to take a smaller cross section of this particular length, if this is the smaller cross section of this length like this, then in that condition the length of this smaller cross section becomes DL. DL means infinitely smaller length. So that is represented by DL. DL is the part of a length that is L. Now the charges distributed along this DL is represented as DQ because the total charges along the length L is Q. So the charges distributed along the smaller part of the length will be DQ. Now the formula will be modified to lambda is equals to DQ upon DL. The unit will remain the same, that is coulomb per meter. So this is the formula when we talk about very small cross-sectional area of a particular length. Now the question arises that if this value or this value gets altered out, no. Why? Because if we are talking about whole length, then charges are uniformly distributed. So Q upon length is a constant quantity. And if we talk about smaller cross sections, so we are taking the smaller part of the length and smaller part of the charge. So in that condition again the lambda becomes constant. So these two values does not differ because the charges are uniformly distributed over the length, that is L. Now the second topic is surface charge density. So what is charge density? Charge density is charges per unit dimension. If the word surface is attached to it, so it becomes charge per unit surface. What is a surface? Surface is a dimension of particular area. In this, suppose this is a rectangle. Now the charges are distributed uniformly all through this rectangular area. Now if I have to consider the dimensional area, then let us represent it by capital A. Capital A represents the area of a particular dimension. In this case the dimension is a rectangle. Now the charges that are distributed uniformly across this area is represented by small q. So q are the total charges that are distributed all over the surface, which is your rectangle. In this condition the surface charge density is represented by a sign. Now what is the formula for it? This formula is again the same formula, that is charge upon. In this case the dimension is changed. In that particular condition the dimension was linear, so we represent it by L. In this condition the dimension is surface, so now we represent it by an area. So this is charge per unit area. Now what will be the unit in this condition? The charge unit is coulomb and area unit is meter square. So now the surface charge density unit is coulomb per meter square. If in this condition I modify it somewhat, that is if I take a smaller part of a surface, then how it is represented? Look here. This is suppose a smaller part of a surface. Okay, the surface is whole rectangle. I took only a smaller portion of it. That portion is represented by the area, let's say dA. dA represents a smaller part of the area and the charge associated with this area becomes dQ. Q. Now again the formula for surface charge density is dq upon dA. The unit remains the same, that is coulomb per meter square. So this formula is applicable only when smaller portion of a surface is considered. Now comes the third part, that is volume charge density. In this condition, the charge is considered per unit volume. Now, how the volume is found? The volume is only calculated when there is length, breadth and height. Let me consider a cuboid in that condition. If suppose this is a cuboid, okay, with proper length, breadth and height. So in this condition, the charges are uniformly distributed along this cuboid. Now, the volume associated with this cuboid is capital V and the charges are uniformly distributed across all the section which is represented by small q. Small q is the charge which is uniformly distributed across volume capital V. Now, in this condition, the volume charge density is represented by a sign, that is this. Okay, the formula for it again the same, that is small q upon, but in this condition it becomes capital V. Capital V represents the volume. So what will be the unit for that? The unit now modifies to coulomb per meter cube because the unit of volume is meter cube. Now, this is when we talk about whole volume and whole charge distributed. But if I talk about smaller cross section of the volume, then the formula modifies to, in that condition, first let me cut out a smaller portion of a volume. Let's say this. So this would be the smaller portion of a volume. In that condition, the charge associated with it becomes dq and the volume associated with it becomes dV. So what will be the volume charge density? The volume charge density modifies to dq upon dV and unit remains the same, that is coulomb per meter cube. So this is the formula when we consider a smaller part of a bigger cuboid. Now the next topic related to this charge density is force on charge due to continuous distribution of charges. Now we have to find the force which is exerted by the linear charge density, surface charge density or the volume charge density to that of the point charge. This point charge is separated by a distance small r. So let us first consider the case of linear charge density. Now, let me first draw a particular conductor of length, let's say small l. So this is a conductor of length small l. Now, a smaller part of this conductor is cut out. So this smaller part of the conductor now becomes dl and the charge associated with this is dq. Now, there is one point charge which is located away from this conductor of length l. Let's say this charge is represented by Q naught. This is a point charge and the distance between Q naught and dq is given by small r. So this is what we have to find. We have to find the net force at point Q naught by the dq. dq is the charge along length dl. Now in this condition, if we are talking of smaller charge, then the force exerted on Q naught is also very small, that is df. df represents the smaller part of a force. Now apply the Coulomb's law in this condition. The Coulomb's law states that df, it becomes df because we are talking of the smaller charge. Then the constant 1 by 4 pi epsilon naught q1 into q2. What is q1 in this condition? The q1 is the charge that is forcing q naught in another direction. So q1 becomes dq. So put the value, that is dq. And what is q2? q2 we can take as q naught. Okay. So this is q naught upon the distance between dq and q naught. The distance between dq and q naught is r. So this is r square. This is a vector quantity. So we need to mention a r cap, that is a unit vector. Now you see from this equation, if I have to find the force, then we need to integrate both sides of the equation. If we integrate both sides of the equation, then on integration the differentiation is eliminated. So it becomes only capital F with a vector quantity on top of it. Now this is integration. All the constants which are not a part of integration is taken out. This 1 by 4 pi epsilon naught is a constant. So it is taken out of the integration sign, again q naught is also constant, so in that condition this q naught is also taken out. What we are left with? We are left with only dq upon r square and a unit vector. Now in this condition you see that dq has a particular formula. What is the formula for dq? If you remember, then for linear charge density we derived the formula that is dq upon dl. So from here we can deduce the formula for dq, which becomes lambda into dl. Now this particular formula is placed in this equation instead of dq. Now putting the formula, you will get the force, that is q naught upon 4 pi epsilon naught. Integration dq is given by lambda into dl, so put the value lambda into dl, r square r vector. So this would be the formula when we take the case of a linear charge density, and this is the force which is applied on q naught. Now comes the calculation of force in the surface charge density. So in this condition, first let me draw a surface. This is a whole surface, okay. Now we have to consider a smaller part of a surface. So this is a very small part of a surface. So let us represent that this particular surface is having a charge dq, and the area of this smaller part of a surface is represented as dA. Now there is a point charge, let's say q naught. This charge is placed at some distance from this smaller section of a surface, and what is the distance between these two charges? It is r. That is the distance between dq and q naught. Now you have to find the force on q naught which is exerted by the dq. As dq is a smaller charge, so the force exerted on is dF. So again use the Coulomb's law in this condition. The Coulomb's law is dF is given by 1 by 4 pi epsilon naught q1 and q2. In this condition q1 is dq and q2 is q naught upon r. R is the distance between the two, so it is given as r square, and it is a vector quantity, so we represent by a unit vector. Now we have to remove the differentiation sign because we have to find the total force. So integrate both sides of the equation. You will get capital F is equals to, take the constant out of the integration, that is q naught upon 4 pi epsilon naught is taken out of the integration. Integrating, you will get dq upon r square with r vector on top of it. Now again, in the surface charge density, there is a separate formula for dq. What is the formula? We have calculated out that this particular surface charge density is given by dq upon dA. So what is the formula for dq? It becomes surface charge density into dA. You have to put this formula into this equation. You will get the force at point charge, that is q naught. So it becomes q naught upon 4 pi epsilon naught integration dq, that is surface charge density into dA upon r square. This is a vector quantity. So this is the formula in the case when we talk about surface charge density and the force which it exerts on the point charge q naught. Now the third is the volume charge density. In this condition you have to find the force at point q naught. In this case I have drawn a cuboid with certain volume, that is capital V, and the whole charge which is distributed inside it is represented by q. Now a smaller part of the volume is taken like this. This is a smaller block of this volume, and the volume of this is dV, and the charge associated with this smaller part is dq. Now if you have to find the force at point q naught, so in this condition again the line joins dq and q naught is represented by r with a vector on it, and you have to apply the Coulomb's law. All the procedure will remain the same as we have done so far. You only have to put different values of dq for different cases. In the case of linear charge density, the dq is different. In the case of surface charge density also the dq is different. So if I talk about the volume charge density, then dq in this condition becomes volume charge density into dV. This is the formula that we have already done. So you have to put this value in this particular formula. So you will get the force, which is a vector quantity, q naught upon 4 pi epsilon naught integration instead of dq, put volume charge density into dV upon r square with a unit vector. So this is the force in the case of volume charge density. So this is what we have calculated for continuous charge distribution.